I got the nice introduction from you, but I just give you a little bit about more. And then relativistic quantum chemistry, the core of it, it's basically based on a class that or module that I give occasionally. So I have shortened it a little, but I haven't completely timed it. So I think it fits in the allotted time, but if not, then we'll rush a bit. So bear with me in that way. And then, as we also said, I give a brief or very brief overview of ADF AMS. So that's the idea. Okay, well, we are right here in Winnipeg, basically in the middle of the North American continent. And that's where we are in Manitoba, Winnipeg. It's east-west in Canada, pretty much exactly in the middle, and in the overall continent also pretty far. We are a northern country, so we may see northern lights like this, at least if we get out of the city. We may, if we go out of the city, we have wilderness, so we may encounter a bear like that, or now it's moving by itself. We get good winters, but we also sometimes, well, we also have summer, so that's not my picture as opposed to the others. This is the center of our campus in summer, or in early fall actually, with some older and some newer buildings. And this is the chemistry building where we work if we don't work from home like today. Right, and here's a little bit of an overview of what we do, all computational chemistry, as I understand you do. So I put our trusted Greg supercomputer here, and current or recent topics, not all of them are active at this time, but for the last few years, we are pretty interested and have been consistently interested in actinide chemistry. By now we have covered the whole periodic table, but maybe focuses on most of the time on uranium through plutonium, or maybe americium, more recently on actinium for targeted radiation therapy. We have been interested in materials. Right now we still do two-dimensional materials. Previously we have done conducting polymers. We have a new project on metal organic frameworks. That's not currently active. We have collaborated with environmental chemists on both crude oils, what happens, basically some thermodynamic parameters, if an oil spill happens in the Arctic, or on mercury chemistry. I'm also not that active solar energy conversion right now. We do a little bit on singlet fission still. And we do method and code development. If I have the time, I'll briefly come back to that. Sources, I got material from Luke Fischer, who is from Amsterdam, and as I said, knows way more about this than I do. And I use somewhat this book here. Here's the one by Ryer and Wolf. I use some of that. I was also earlier saying these slides are taken from a module that I occasionally give, and I have shortened it a bit, so I'm not entirely sure about the timing here. So we'll see. If I run way too long, just yell and let me know. Another source is this book by Jochen Autschbach, who's at State University of New York in Buffalo in the United States. Here he is when he published the book, and chapter 24 is on this topic. Quite a good write-up, actually, quite a really good book on quantum chemistry in general. Okay, relativistic effects, following Autschbach here. So we ask the question, what are they? What do we mean by that? And then we ask the question, does it matter? Is it relevant for chemistry? Perhaps not. And if it is relevant, why would it be relevant? And then we see, how do we do it practically? That's basically the program. Okay, so you're probably familiar with the model chemistry graph that goes back to John Popel, where we put the correlation method on one axis and the basis set on the other. And of course, the aim is to get as far as possible towards the top right corner here. And on the correlation axis, as I'm sure you know, we can do ab initio, we can do DFT. As you have done the last couple of days, we can do semi-empirical methods. Now, for the basis sets, we can have Slaters, Gaussians, plane waves, etc. Now, if we're talking about heavier elements, the lower part of the periodic table, this two-dimensional consideration is perhaps not good enough, and we have to go to a third dimension, which we can define as relativity, and that would be a third dimension. So here's my extended graph, and that's what we will focus on today. So it's not strictly a DFT topic, it's more a general topic that's kind of orthogonal to these others. Maybe there are cross terms, but in general, we can view it as orthogonal. Before I go to that, just digressing for a moment, for the last 15 or so years, I've used this as an organizing principle to say, well, maybe there's yet another dimension, which I call complexity, in terms of computational modeling. And what I mean by that is that if we do computational modeling, what we want to model is inherently quite complex, and we have to simplify this and choose a model. And so here I've pulled the model chemistry and the first two axes into one so that I can still draw it. And this is crucial, I think, for materials, but also for various other situations. We need to choose a model for solvation for things like conformational space in solids or surfaces for defects, interfaces, different length scales, etc. So that's kind of just my view of how I like to organize these methods that we use. Anyways, back to relativity. And I just need to go over here and look at my notes that I don't forget something. There's a relativity principle which actually goes back to Galileo and not, so it's not strictly what we would call relativity. And it poses that physical laws should be the same for all observers, such as Newton's first law and so on. And we'll come back to that. That concerns in particular the inertial frame that I'm in. And if you, as another observer, are in an inertial frame that moves with a constant velocity relative to me, physical laws should be the same. That's a relativity principle that applies to Newton's mechanics also. So all initial frames are equivalent, and Newton's laws have the same form in all frames. So we can't single out a preferred inertial frame. That's not what we typically call relativity. Instead, what we call relativity is typically what one might call Einstein relativity, which has special and general relativity. Here in chemistry, we only are concerned with special relativity. So then in that, typically the Galileo version and Newton version, we would refer as non-relativistic, and that's what I will do the rest of this presentation. So Einstein relativity. One can define them as the effect of a finite constant speed of light, I'll come back to that, compared to a hypothetical and unphysical value of infinite, of infinity for the speed of light. And in atomic units, theoreticians like atomic units is 137 atomic units, inverse of the fine structure constant. In SI units, it's something like 299,792 meters per second in vacuum. And it's constant in all inertial frames. So we'll come back to that. As we will see, the Schrödinger equation is no longer valid under these conditions, and so we would have to modify it. But back to the question, does it even matter? Do we have to do that? And this is not trivial. The great Paul Dirac himself, after he published the Dirac equation, had made this statement here. It's quite long, but I'll go over it. It's well known as Dirac's dictum and often quoted. So he says the general theory of quantum mechanics is now almost complete after his Dirac equation. The imperfections that still remain being in connection with the exact fitting of the theory with relativistic ideas. These give rise to difficulties only when high-speed particles are involved, for sure. We need high velocities close to the speed of light. And then I've highlighted that he writes, they are therefore of no importance in the consideration of atomic and molecular structure. So basically, Dirac is saying it does not matter to chemistry. And I'll come back to why he says that in a moment. Okay, the quote goes on to say the fundamental laws necessary for the mathematical treatment of large parts of physics and the whole of chemistry are thus fully known. And again, it's my highlight here. The difficulty lies only in the fact that applications of these laws leads to equations that are too complex to be solved. That's, to me, this part in blue is the program of what we as a quantum chemistry community are doing. We find approximations to deal with these complex equations. Okay, good. So does it matter? Dirac is saying no. And why is he saying that? Well, look at, say, a hydrogen-like atom, Schrödinger. You get an atomic unit that the energy of level is z squared over 2n squared. And you can make a back-of-the-envelope calculation using the virial theorem to realize that the average velocity of the electron is proportional to z over n. Okay. let's take something heavy, such as mercury, Z equals 80, and we take the 1s state here, n equals 1. 80 is pretty close to 137, which is the speed of light. It's an appreciable fraction. So for the 1s electron of mercury, these effects should definitely matter. However, chemistry is not done by the 1s electron of mercury. It's done by valence electrons, and valence electrons are shielded and have much lower average velocities. So that's basically where Dirac is coming from, saying because valence electrons make chemistry and they're on average slow, then it shouldn't matter. So here we are. Valence orbiter. Sorry, I was too fast here. I'll come back to that again in a moment. Here are some slides still from Fischer, so this is what I said. The velocity is close to the speed of light. I was kind of ahead of myself. Here are some examples from Fischer, who says it does matter. He calls that, this slide here calls visible relativistic effects. It turns out that in solid gold, the 6s orbitals are significantly stabilized relative to the 5d orbitals. And so that moves the transition from UV to the visible. And so we can see in the yellow color of gold, we can see relativity, basically. Non-relativistic gold would be metallic, like silver. Or we see relativistic effects in things like phosphorescence, because singlet, triplet intersystem crossing requires spin-orbit splitting, which is strictly forbidden in non-relativistic quantum mechanics. But these kind of transitions are weakly allowed in relativistic quantum mechanics and kind of in nature. Another visible effect that I don't have on the slide is that mercury is a liquid at room temperature. Again, non-relativistically, it wouldn't be. Here are some slides again from Fischer, what he calls it orbital stabilization. I think what he means is a negative of the orbital energy. You go down the periodic table in some period here. Some group here. And you should get that the 1s, you should get that the orbitals, orbital energy should go up like less than negative. What you see is that this kind of curved line. This is also shown, this also goes out into electron affinities, ionization energies. You have this kind of shape here. I pulled this from Wikipedia. Whereas non-relativistically, you would expect a monotonous trend, just because you go down and down the periodic table. If you go to like orbitals that contain where the valence electrons are p, you get a splitting of the energies, and for d also. And so for p, one is stabilized, the other is not destabilized, p1 half versus p3 halves, compared to non-relativistic. For d, there's only mostly a destabilization. And then if I get a trend in stabilization of s orbitals, that's also shown in the size, because the size is basically of the, in this case, the size would mostly be determined by the outermost s electron. So it shows up in the size also, where you would, if you go down the periodic table, you would expect a monotonous increase in size. That's not what you see. And again, here, this is pulled from Wikipedia to show the same thing. On the other hand, P kind of split and expands and contracts, as we saw in energies. D does expand. Right, and again, I need to make sure that I stay with my notes here, so that I don't get ahead of myself. This one I really like. It's old work that I did. Part of it I did during my PhD, and others also. If you go 3D, 4D, 5D, you get, for any kind of properties, bond lengths, first bond dissociation energy, and so on. You get these kind of typical triangle-shaped curves here, where the 4D element is the most like kind of most weakly bound, and 5D is more strongly bound. Again, clearly a relativistic effect. Right, where am I? Or this one is also nice. It comes from Pekka Pöke, who's a pioneer, or was or is a pioneer of these things. And they calculated the voltage of the lead acid battery that starts, or cars, at least until we go to electric cars, but the kind of regular cars, right? And that lead acid battery, sorry, has a voltage experimentally of 2.11 volt, relativistically calculated, best calculation 2.13 volt, pretty close. If you calculate it non-relativistically, it's just 0.39 volt. So Einstein, that's where the cartoon comes from. Sorry, not Einstein, Picke, where this cartoons comes from. He says, we start our cars with relativity. So these are just some examples that it apparently does matter. So coming back to this question, why is that? Because as I said, valence orbitals are slow and they have only a very small fraction of the speed of light on average. There's two explanations that valence orbitals are orthogonal. So 1s sees very strong relativistic effects, is contracted relative to non-relativistic calculations. So is then 2s, which is orthogonal, 3s, and so on. So it triggers through. More recently, the one that I highlighted here in orange has been brought forward, and that seems to be the right explanation. It's true that, say, the 1s orbital or p, 2p, and so on has a low average velocity, but there are still core lobes. So it still has a finite probability of being close to the nucleus, and that alters the shape even of, say, a 5s orbital. Okay, so overall, what we see S, especially to some degree P, are stabilized relative to non-relativistic calculations, and contracted. D and F are destabilized, and that pushes through to molecules and so on. And then there's spin orbit that I mentioned, for instance, for interstitial crossing and all kinds of other spectroscopies. And for very heavy elements, it also matters for structures. Okay, here's a little bit of a timeline as per Fisher. Special relativity came first in 1905, Albert Einstein. The Schrödinger equation comes in 1926 with quantum mechanics and parallel as matrix mechanics, so 1926. Already in 1928, Dirac published its extension to like the one electron equation, the Dirac equation. And in 1949, quantum electrodynamics kind of concluded this. My physics colleague told me the other day, oh, it's interesting, anybody's still using the Dirac equation. It works well for us in chemistry. In physics, they pretty much do quantum electrodynamics. But for us, Dirac equation or some approximation thereof is still pretty good. Okay, so let's go into this a little bit. Again, this relativity principle that I already mentioned. As I said that already, all inertial frames are equivalent, which means that the Newton's laws of motion must have the same form in all inertial frames. Right. So here they are. Consider two inertial frames in one dimension here, x and x prime, and x prime is moving with a velocity relative to x. Right, and then one can look at what happens if one wants to transfer some physical process from one to the other. And that's summarized here. The time differential is the same in Galileo or Newton's mechanics. So dt prime is dt. And then x, if you work it out, x is x prime plus vt, right? So one has to position and one has to account for moving of this inertial frame. I'm not totally sure that this slide and the previous slide agree with the sign, but the principle is there. So x is x prime plus vt, and in this example, the other frame was moving in the x direction, so y and y primes, they are, and z prime are each the same. So now if we look at velocities, we take the time derivative here, and so basically we get an addition of velocities, which for intuition makes sense. You have to add the velocity of the frame moving. Say, if you are in a train and the train moves with 100 kilometers per hour and you're walking in the train with 5 kilometers per hour, then relative to the landscape outside, your velocity should be 105. Makes sense. Intuitively, it makes sense. So addition of velocities. Okay, now, though there's nature. This is a thought experiment. Again, it's Fisher's slide here. Consider a double star pretty far away. There are the astronomers know that there's such a thing. And I quickly stop sharing. I have my document camera over here. So I make a sketch here in just a moment, and then I go back to the slides. And for that, I need to replace my face with the document camera here. So here we are. So here we are on Earth, and Earth is rotating, and over here is my double star. And it's far enough that we see only one star in principle, right? But we know it's a double star from the clever experimentalist. And so it's rotating. And so there's a time point when this one part of it is moving away from us, and the other one is moving toward us. Right. Okay, so then we would have the light would some many years, depending on the distance, reach us. And because one is at this time point moving away from us and the other towards us, we could say the light might have velocities of v plus c and v minus c. Oh, here's a cat visiting. That's the joys of Zoom. Okay, cat, maybe you can go out of the way. Okay, good. Yeah, you don't see her anymore. So that would be this from Galileo transformation, basically. But I put a big question mark here. Because if that were to happen, and also the Earth is rotating, we should see the double star in two different positions in the sky, because the light would hit us at different times. Okay, no, that's not what, yeah, that's back to my face and share screen. Where are we? Yeah. So do we observe one star at two different positions? Because as I said, the Earth has rotated when the light hits us at different times. That's not what we observe. So we have to conclude that the speed of light is a constant. Then people proposed that there is something called a ether or luminiferous ether. So basically there's some kind of substance that would supposedly carry the light waves like this. And if that's the case, then there might be wind in this, and that might determine really when the light comes to us. There's a really ingenious experiment, you can look it up, the Michelson-Morley experiment, that looks at that, basically looks at light in different directions and at different times, because if there's that ether wind, then it should hit us relative to Earth different here in the spring than in the fall or something. Again, no, there is apparently no such thing, and so we have to conclude that the speed of light is a constant, independent of the inertial frame. And that's quite amazing in some ways, because again, it contradicts our everyday experience. And it has some consequences on that transformation that we had. It leads to special relativity, basically. Here's my speed limit for speed of light. I don't know, I think the cartoon is also from Fisher. Okay, so another thought experiment. Again, we do what we did before. Two observers, one on the train, the other outside. And they're right past each other, and I might sketch it here, but maybe you can imagine this. But there's a tunnel nearby, and the sign of the railroad goes on, and it sends out light, and it hits the entrance to like basically the wall or the entrance to the tunnel. So the speed of light is a constant, and so then they have to figure out when the light that comes from the sign hits basically the wall of the tunnel. And so one is moving. Yeah, so the one standing there says distance over speed of light, fine. But the other one is moving. The train is moving, so he has to conclude the tunnel is moving towards him, or he towards the tunnel, so he gets a smaller time. So if we have to conclude that if the speed of light is a constant, then time has to depend on the inertial frame. Right. And so here's the math to it. I'm not gonna go over it in any detail. You can go into the books and do this. But this is if the time, if c is constant but t variable, that's what you have. Here's our Galileo transformation in one dimension. That wouldn't work. That wouldn't do this. So we make an ansatz here. We add some scaling factors, gamma and alpha and beta. And if we plug them back in, basically what we find is that gamma is this, 1 over square root of 1 minus v squared over c squared, and beta is v over c squared. And that's the Lorentz transformation. And you can generalize it through 3D. We don't have to do that. We can make an immediate test for consistency. If C is very large compared to V, voila, we are back at the Galileo transformation, T equals T prime, X equals X prime plus VT prime. Wonderful. So we need to, in that limit, in the non-relativistic limit, we need to get back to this. Good. So that's a Lorentz transformation. That's still kind of macroscopic stuff, basically, right? In terms of the Schrödinger equation, as I'm sure you know, if you write the time-dependent Schrödinger equation, you have a first derivative with respect to time, but a second derivative with respect to position. And that basically is not compatible. If you transfer and then time transfers it to position and vice versa, they have to be at the same level. So Schrödinger equation is not compatible with the quantum with special relativity, as I kind of said on earlier. It's not valid anymore. It cannot be Lorentz invariant. And that's the relativity principle. It has to be have the same form, no matter whether I'm on the moving train or not. Another shortcoming is spin is certainly known experimentally, but we can only introduce it ad hoc, and there's no spin orbit coupling. This is also known experimentally. Okay, so there's that Lorentz factor, just a little bit of background that I showed you. Oftentimes we expand it. That's often useful to expand it. Again, I'm not going to spend much time on that. But if you do that, you get, for instance, momentum. So you get the non-relativistic momentum as a leading term and then corrections. You get the relativistic mass increase, where m is the rest mass of the particle. So if you have a finite mass and the velocity approaching the speed of light, the mass diverges. That's exactly why we can't accelerate a finite mass particle to the speed of light, only close to it. So these are the kind of things that are in there. We can even do that for the energy. That's interesting. It gives us the non-relativistic kinetic energy, but as a second term. The first term is the relativistic mass, rest mass energy, basically. Right, where am I? Yes, so it's a rest and mass energy. Like if we take a relativistic limit by letting C go to infinity, we have a bit of a problem. So typically what people do is we shift the energy scale first to set the zero such that this term is zero, and then we do the expansion. So that's what I just had here. Okay, quantum mechanics. As you might know, to get to the Schrödinger equation, there's what Auerbach calls the quantum recipe, basically writing the classical energy expression, which for the Schrödinger equation is the Hamiltonian formulation of classical mechanics, and then quantize. The position representation, that's how we quantize. Right? So can we do the same for quantum mechanics, starting with a relativistic energy expression? But anyways, here's our Hamiltonian with spin. So can we do that for a relativistic expression? Here it is. If you look at it and you want to put in here the momentum operator for position, for momentum, the momentum operator with its derivatives, you have a problem because you have a derivative under the square root there, right? Derivative under the square root. What does that even mean? So that's a real challenge. So what do we do? Well, one thing is maybe we square the whole thing. Yeah, that's what I just said. How do you quantize a square root? You might expand it and then quantize, but it's tough. So maybe square and then quantize. That has been done. It works. It does not have spin, so it's the so-called Klein-Gordon equation. It does not have spin, so it's no good for electrons, but it works for mesons. Here I have it. So squared, time derivative for energy, spatial derivative for momentum. So it does work, but again, it's not good for electrons. Right. Where am I? Here. So Dirac's genius was to basically make a different ansatz or a different square root. And so basically he writes, it's an ansatz. Kind of let's take the square root of each term separately, but introduce something here. beta and alpha is a vector. This is a vector product here. Right, so it has 3 components. If we do that, we can work it through and say, now let's square it and then make sure that the left and right hand side are the same. And that leads to some conditions of what beta and alpha might be. But we could quantize here, and that actually is the Dirac Hamiltonian. Right, here's the kinetic energy, we add the potential. But otherwise, we can quantize that. So what's the meaning of these things? Again, here, this ansatz. So we square this kinetic energy expression, assume that P commutes with these things, with these alphas and betas. And then what we do, then that tells us what beta and alpha need to be. Basically, beta squared, for instance, needs to be 1 for this to be equal. This stuff needs to be 0 because there's no such term on the left-hand side. And this, I think, yeah. No, that's good. Yeah, and this here also, this term needs to agree to this term. So we compare the left and right-hand side, and that tells us that there are these anti-commutator relationships for these alphas and betas. The things, in principle, one could stop here and say, that's my theory. In practice, one wants an actual expression, and one realizes that one need matrices to do this. Because matrix products in general don't commute. And so the smallest representation that does these anti-commutators are these Dirac matrices that are 4x4 matrices. Here they are, beta, X, Y, and Z components of alpha. So here they are again. We often write them in a block form, so where we have them as blocks of 2x2 matrices, like this. For instance, this is the unity matrix here, 2x2, and minus unity matrix. Here's the 0 matrix, and so on. We can do the same for the alphas. And then we realize, voila, on the off diagonal here, we have the Pauli spin matrices. Sigma X here, sigma Y here, and sigma Z here, basically. So that's quite interesting. So this in the block form, it looks like this. And again, where the bold means it's a vector, like a 3-dimensional vector. So then it gives us a Dirac Hamiltonian. We can write it with these beta and alpha here. We can write it in this block form, and that's how it looks like: V plus MC squared, V minus MC squared. Right. So and again, these are operators here. So this Dirac Hamiltonian is both an operator kind of thing with the derivatives, but it's also a matrix, which means that the wave function needs to have 4 components because it's a 4x4 matrix. 4 components. That sounds weird, but it's not that weird, because if you think of a spin wave function in principle, if you include spin, there you have 2 components, spin up and spin down, right? And both are spatial functions. So here we have 4. And so here's the Dirac Hamiltonian written out, slightly different here with phi for electric field and pi for the vector potential of a magnetic field. So with electric and magnetic field, not going to spend much time on it, just to note that we include the magnetic field by way of minimal coupling. Anybody needs more details on that, again, it's in the books, or we can discuss it at some point. We see, did I forget anything? No, here we are. Good. I'm not going to go over this. Okay, let's look at what this Hamiltonian looks like. Here is, for instance, a free particle, potential equals 0. And again, it's written in the block form. So each of these are 2-component wave functions. And if moreover, if you have a particle at rest, then both of these terms disappear, and we can look at, I only left with a beta here, and we can write down plane wave type of solutions with a or oscillating kind of time dependence, as we would do in the Schrödinger case, basically. And when I do this as a class, I ask the students to verify that these really are solutions. But that looks pretty similar to what we do when we go from the time-dependent Schrödinger equation to the time-independent Schrödinger equation. And in particular, we notice that in here is basically the energy, just as in the Schrödinger case. Right? And so we have positive and negative energies. That's what we get out of here. Positive and negative energy solutions for the free particle at rest here. If you extend it for a free particle, not going to go over it, but you can make a plane wave ansatz and so on. And again, you get positive and negative energies. So that's a result basically of this four-component ansatz that we had. We get positive and negative energy. So we should ask ourselves, what does it mean? Or does it have any physical meaning? And maybe not. And so basically, we have here the rest energy, MEC squared, and that thing squared, but it's under the square root. And then we have momentum and plus minus, basically, right? So that's basically how it looks like. Plus MC squared minus MC squared. These are free particles. And we might have extra bound states here. But we have this. And in the middle, we have E equals 0. Or rather, W equals 0. That's an ouch bus notation. Here is a shifted energy scale. But anyways, we have positive solutions at rest mass energy MC squared, negative solutions. Okay, where are we? Here. Okay, one of the things, if that's the case, is a problem for how we do quantum mechanics, because typically for quantum mechanics, say if we have a bound system like a molecule, we use our variational principle and says, of course, that the ground state energy is basically, or the ground state wave function is that wave function which gives us the lowest possible expectation value. If we have negative solutions and for basically infinitely many of them or something, well, then if you do a variational calculation, we just go more and more negative. So that's a problem. What does this mean? Yeah, that we call that variational collapse, because basically our variational principle collapses into the negative continuum. Right. So what's the physical meaning of this? Well, what Dirac proposed is that all of the negative states are filled, and we call that's called the Dirac sea. So there's basically infinitely many filled states, all state, and we have the Aufbau principle and the Pauli principle. If they're all filled, then yeah, with the Pauli principle, then we can't have double occupancy. So then we need to start filling the positive states. That's an interesting proposal. Yeah, there we have all negative energy states are filled, Pauli principle. That's an interesting proposal, and that has physical consequences, because if true, then we should be able, if we have enough energy, to take an electron and excite it by 2 MC squared from the negative to the positive continuum, like that. And that would leave, if so, that would leave a positively charged hole here. So here's an example from Fischer, same thing. We have a system, say H2, with 2 electrons. We should be able to take an electron out of the negative continuum with enough energy and excite it to here. So there's a Dirac sea, and there's that cartoon. So if there's a positive hole here, because we have excited an electron, that should lead to a positively charged particle. Right? That's what the theory proposes. And that would be the positron, and it was indeed discovered in 1933. So that was a huge success of this theory. It predicted the existence of the positron, and it kind of was a real verification of this theory. Nevertheless, the theory has its drawbacks. An infinite background charge, it's not good, really. Quantum electrodynamics in the late 1940s dealt with this. Basically, it replaces the kind of picture that I've just drawn by second quantization, creation, and annihilation operators. That's beyond what I know and beyond what we could do here. But basically, you describe your state in an n-dimensional Fock space by occupation numbers, and so vacuum would be all states have an occupation number of 0. And you have creation and annihilation operators and so on to create electron-positron pairs. And then you can define all operators in terms of these and so on. That would need to include photons, and so it's way beyond what I really know. More to the practical things for quantum chemistry, we need electron-electron interaction, which we do with the Coulomb operator as we know it, at least to first order, because the speed of light is finite in principle. There's some retardation by the finite speed of light, so there are corrections that can be added. They're known as bright correction and so on. So that can be done. Yeah, here are the bright correction terms. So here's my first order interaction as we know it, and there are various other terms that one can add. These can be added to the Dirac Hamiltonian. I have never tried that myself. Right. So Coulomb term, so-called Gaun term, that comes from the so-called Zitterbewegung and this retardation here. Okay, so positron, discovery of positron, real confirmation of the theory. Second quantization deals with the infinite background charge. The theory should also contain the Schrödinger equation because it does work for light chemistry and for all kinds of things. So it should be contained as a non-relativistic limit. Here we are with our Dirac equation. The problem we have is if we let go to the non-relativistic limit and let C go to infinity, then we might get divergences in these kind of terms here. Oh, and here it's written in the shifted energy scale. And here are the two equations. And I didn't go into this, but we call the upper two components, we call the large components for electronic states, and the lower two components we call the small components. That's what the superscript here is. Because again, for electronic states, these are an order of magnitude smaller than the other ones. One can show that. So we can substitute here and then do the limit. This factor here, again, I'm not going to go over the mass, but then do a Taylor expansion basically, and that gives us non-relativistic limits. The method is known ESC, elimination of the small component, by inserting this transformation into the upper equation. That's kind of that's what it looks like in to zeros. Sorry, that's what it looks like. There's a factor in here, and the problem is that this operator is energy dependent because we had. If I go back here, if we connect one of the two, here there's the energy in this little k here. So the operator is energy dependent, which makes it difficult, and one has to make additional approximation. But if we let C go to infinity, then the k is simply 1. And we are nicely left with our Schrödinger equation, but including spin. So that's another real success of the theory, that spin just appears out of it. It arises naturally. Let's look at the time. I think, yeah, we are good on time. I didn't watch the time at all. I just kind of kept going here. Right, so we get the spin. We get the Schrödinger equation out of the Dirac equation, which is good. That's what we want. If you have a new theory, it should encompass the older theory and expand on it. And again, spin arises naturally. So that's a real success. Right. We prefer two-component methods because it's less work, and we ideally can use our codes as they are because they are written for two components, methods spin up and spin down. So we can use all the tools that we have in the codes, be it geometry optimization or property calculation or analysis or what have you, right? So two-component methods are useful. Typically, you would take that Taylor expansion here and keep some order of it. So like this, for instance. That's a quasi-relativistic Hamiltonian, is still the energy here. But that's you could do that. And so we have a non-relativistic Hamiltonian, then we have a correction to both kinetic and potential energy, and we have a spin orbit term here. Spin and orbital angular momentum coupled. That's quite typical for these. The oldest of these, slightly different, is a so-called Pauli Hamiltonian. It's based on the Foley-Wauthuysen transformation, way back when I was a grad student, I once worked through it, but it's tough. It's quite a complicated derivation, so I wouldn't be able to do this anymore. But it has all these contributions, or a non-relativistic Hamiltonian, a correction to the kinetic energy, a correction to the potential energy, a spin orbit term. So this one we call mass velocity. We call that one Darwin. And we call these scalar because they do not contain spin, and then spin orbit. This one is nice because it has like conceptually shows what these terms are, but it suffers from this variational collapse that I had mentioned before. We could use it, but only very carefully with carefully curated basis sets and what have you. So it's not really used much anymore. There are other two-component Hamiltonians, again, based on that expansion here. One trick is to rewrite this K factor here, because we realize that the potential here, say for, like by doing the expansion, we assume that this K factor is small, like by doing a Taylor expansion. But if you take a typical, say, hydrogen atom or any atom, the potential is 1 over R. That's our typical nuclear potential. So close to the nucleus, this is not small at all, right? So close to the nucleus, and that's actually where the problem of the Pauli Hamiltonian comes from. So one approach was to rewrite it just by mass, such that the potential is now in the denominator, and even now close to the nucleus, where it gets numerically very large, it's in the denominator, so the K still stays small. That's a kind of clever trick, and then do the expansion of this here. And if we say, okay, we are lazy, we do the expansion only to zeroth order and to neglect any higher orders, that leaves us Zora, zeroth order regular approximation for relativistic effects. And that's a very valid relativistic method. It was developed in Amsterdam by Erik van Lente in his PhD thesis working with Eva-Jan Barents and others. And so here's the Zora Hamiltonian. The capital K is the one from the previous slide. So kinetic energy here, and potential energy unchanged, and a spin orbit term. So that's a standard relativistic method. It contains a non-relativistic limit, and so on. It's a good relativistic approximation for valence properties. It's a little less good for, say, core shells, but it's being used quite extensively. Autschbach has a more detailed discussion of that. So Zora is used quite extensively. We can introduce magnetic field, do things like NMR, and so on. And it is in various codes, including ADF, NWChem, ORCA, and probably others. There are other two-component Hamiltonians that do slightly different transformations, including trying to go to an infinite order. The Douglas-Cole-Hess transformation that's principally used at turbomole, maybe elsewhere. I think ORCA may have it also, that I don't know. From our practical benchmarking, it behaves pretty similar to Zora. That's my understanding. It's perhaps a little more tedious for the developer if you want to develop something new. There are more terms to consider. An ongoing development is to try to develop exact two-component Hamiltonians X to C type methods. ORCA has some of these, ADF has some of these. It's ongoing development. There are some issues that one still has to deal with, so that's kind of the sort that one maybe should stay tuned. Right, I don't have too much experience with these. Let me see where I am in my notes here. Good. Yeah, here's a little bit on these. Oh no, that's just a fun slide. I took that out, the X to C stuff. That's a fun slide from Fischer. He says, if you want to develop a two-component, what should it do? So it should look like the Schrödinger equation, kinetic energy, potential energy, as much as possible, so that, again, we can use the codes that we have. It should describe scalar. Remember, scalar is the stuff that's not spin orbit, and often in practical calculations, often we do we neglect spin orbit if we can. But it should also have spin orbit in, because for some things spin orbit really is very important. It should be variation is still stable, so the Pauli Hamiltonian did not have that. but newer ones like Zora have it. Right. For the developer, it should be easy to implement. And yes, it should be good. It should be correct relative as much as possible relative to the Dirac equation. And ideally, you should be able to improve systematically if you can, right? And then the last one I really like, he said it should have a nice name. Arguably, the name Zora is nicer than Douglas Cole has, but whatever. Okay, good. Where are we? Here, good. So a little bit back to the Dirac equation, because some people do have written codes for it, and we have done, or occasionally we have done calculations with these. If you want to implement it for chemistry, what do you have to consider? Nice thing is you can add these bright corrections that I briefly mentioned. You would also add like a model for a finite nucleus, because the nucleus is finite in size, and that shows that may for extremely accurate calculations may be relevant. We would do the same thing as we do with non-relativistic calculations. We would expand the equation into basis sets. What people have found that one would have to do it separately for the large and small components, but then we can use Slater's, Gaussian's, numerical orbitals, what have you. But one would have to do it separately for the large and small components. And for the correlation, we would use what we know from the non-relativistic cases, like DFT or coupled cluster perturbation C. We would use SCF, etc. Right, continued. Oh, yeah, to say this here, I think I didn't leave the slide in. We need separate basis sets for the large and small components because where am I? I had it on here. Yeah, here, because it turns out that there's something called kinetic balance. We need to go one higher in angular momentum for the small component than for the large component. So if we have a basis set that goes up to D, like 631 D star, then for the small component, we have to go up to F. Otherwise, it's not balanced. And that's kind of frustrating because the small component for electronic states is by definition small, but we have to go to bigger basis sets for that. So it's called kinetic balance. That's what I mean by separate basis sets here. Okay, codes. There's a European code called Dirac, developed by Trond Sauer, Luke Fischer, Hans Jensen, and others. Here they are. There's a code out of Beijing, I think by Wenxian Liu and his group, but I haven't seen it used by anybody else. They call it similar to ADF, Amsterdam Density Functional. They called it BDF, as in Beijing Density Functional. There used to be a code that's probably still around that we used maybe 10, 15 years ago a lot because it was efficient. The Russian scientist Dmitry Lykov called Priroda, but Lykov has moved on to other things and not developed it any further. So we have kind of gone away from it. It was very efficient. It used the Dirac equation, but spin orbit projected out. So it was Dirac equation, but scalar. There's newer development by the group of, I hope I pronounce it correctly, Xia-Zong Li at University of Washington in Seattle, United States. And there are probably others, but these are the ones that I'm aware of. I did leave the slide on the small component. Okay, then I did leave it in, but I'm not going to do the derivation here. So the nice thing, if you use the Dirac equation, is that we, don't make approximations to relativity. It's easy to deal with operators. For some of the transformed methods, it's a lot harder because you also transform the operators, and sometimes it's not clear to do it. It's way more costly in these points. Yeah, picture change. I didn't discuss this, excuse me, but it means that the operators change when you do these transformations, and sometimes it's hard to know what these are. But again, what I already said, I have it in my notes, but I could do it on my document camera, but I think I skipped that, kind of derive why this is that we need different basis sets for small and large component. Oh no, I have it on here. Never mind. So there's a separate basis set expansion. Right, 22. Oh, okay. Yes, now I confused myself. I added some slides and my notes don't correspond to the slide numbers. Anyways, here's the basis set expansion. Large component, small component. And there's the so-called kinetic balance condition, and that, because there's a P operator here, that leads to the requirement that we need larger basis sets for the small component for electronic states. Again, I'm not doing the derivation here in the interest of time, but it's in the books. And yeah, so there's what I said before. I had forgotten that I had left it in. So if we have S, P, and D in our kind of electronic basis set, the large component basis set, then we need to go up to F for the small component. That makes it more expensive still. Right. So if we go to L like D, L equals 2, we have to go to F for a small component. Okay, I mentioned Dirac equation. These were some little aspects of implementation. Another method that people use are effective core potentials or pseudo potentials. As far as I know, the name can be used interchangeably. Here. Formally speaking, that's not a relativistic method because you just add a different potential. But practically it is, because good pseudo potentials or effective core potentials are parameterized to essentially mimic the relativistic effects on the valence orbitals. And so these are valid methods for valence properties. Right. So basically, as I'm sure you know, you replace the core, freeze it, and replace it by a model potential. And this is a well-established, mature kind of field. There are reviews, this one and the one I had on the previous slide. One of the effects, practically speaking, is that we get what's called a pseudo-orbital. I'll show you that in a moment. Right. Namely, if we take, say, our 6s orbital here, we have all these core wiggles. And in this scale here, it looks like this is valence, and that's where bonding happens. But in this scale, or here it is, yeah. In this scale, it's kind of hard to see, but we have all these core wiggles because we have the various nodes in the higher orbitals, right? Because of orthogonality, 1s, 2s, 3s. Orthogonality leads to the nodes. So here, in the density, we have all these nodes here. That's for the 6s. Of course, chemistry happens here, right? So in a sense, we don't really care about this because chemistry happens here. That's the highest density, and that's also kind of from the range where overlap happens and all that. So it makes sense to replace this by something else if you don't really need it. So here's a zoomed in version, but again, this is where chemistry happens. So basically what you do is you create a potential such that you get rid of all of this, and up to some matching point, what's now a pseudo orbital that you use with your ECP looks the same as the actual orbital, and in here it's not. Right? That's the idea of ECPs, and it's useful because, well, you don't calculate all the core electrons, which are not doing chemistry anyways, so you save time, and you can again model this such that the valence orbitals behaves properly in terms of relativistic effects. Here's another example for the 4s on bromine. 1, 2, 3 nodes in the actual orbital, and these are two different parameterizations of what the pseudo orbital could look like. Right. So then the question arises, how much do you put into that core? Like how much do you throw away and put into that orbital? Just to give an example for uranium, this is the valence configuration, and naturally you would say, let's put all of this in the core because it is. But you could also go down one shell down and have way more on the valence and only put this in the core. So this, if we do that, we call this a large core ECP, and that's the small core ECP. And intuitively, you would say, well, why should I carry all these electrons here? Cost me something in their core anyways. They don't change in actual chemistry. It turns out, though, that the small core ECPs are more accurate than the large core ECPs, so that's what I would recommend, actually. We have tested this basically by comparing against for small molecules against for various functionals against the Dirac equation, basically scalar calculation. These are frequencies. We've done it for bond lengths. This is for uranium here. We've done it for different basis sets. We have done it also for other elements, and we see consistently here uranium, but also say mercury, iodine, what you name it. We can see consistently that the small core ECPs are more accurate than the large core ECPs for all kinds of properties. As I said, we tested this for at least these three, probably for others. So it's kind of counterintuitive coming back to my discussion here. So why would this matter? What I think is what happens is if we go back to this picture here, by keeping the first kind of core wiggle here and then only then making it a pseudo orbital, we just get a better description of the valence here, basically. So if we have more core, then my pseudo orbital needs to my pseudo valence orbital needs to be orthogonal to this. So we keep the first kind of core wiggle and only here make it pseudo orbital in this example. So that's where I was. So I think that you get a better description of valence MOs. In my last bullet here, this is we often do solid state calculations with, say, plane waves, and we do solid state calculations also with cluster models of solids with our atom-centered codes, Slaters or Gaussians or whatever. With the plane waves, you really have to take the equivalent of the large core ECP, otherwise it just doesn't work, essentially. So that is a somewhat of unexpected to me anyways advantage of these atom-centered basis sets over plane waves. ECPs can be used to calculate valence, magnetic properties, and so on. The operator can be used as is. You can calculate NMR on neighboring atoms, not for the ones where you put the ECP. You can reconstruct the original wave function. We haven't done that, but it can be done. And you can add kind of spin orbit operators on top of the ECP. So ECPs are a good method here also. Okay, and I think that's it for this section. Before I go to AMS, here's my nice picture of my son many years ago at the Grand Canyon for the end here. Shall we do some questions here?
Sure.
Yes.
And I have another section, as I said, a little bit, just 5 or 10 minutes on the ADF code and AMS software package, but it's like 5 minutes or something.
There are some questions.
Sure, go ahead.
Hi, sir. Nice talk. My question is, how important is this picture change effect if you are moving from the scalar relativistic calculation to the two-component calculation? Do we really need to consider it while doing computations?
Do you need to consider spin orbit? Is that your question?
A picture change effect, PCC.
Okay, picture change and spin orbit and scalar are two different things. Picture change happens, and I haven't worked it through in detail, but it happens if you do some kind of transformation. This is basically up to the developer to try to get this in. Basically what it means, or at least my understanding, and it's somewhat limited, but my understanding is that the operator really takes a different form as soon as you do this transformation. And yes, ideally you would include that, but again, to some degree, that's up to the developer. In practical applications, the methods that we have, like Zora, they kind of do that. But again, that's the limit of my expertise. I don't think I can really get into any details here. I'm sorry, but it's a good question, though. But I mean, ideally, you need to consider it. Practically, you make compromises, as you always do in quantum chemistry. That's my understanding.
Yeah, okay. Just I want to know, like, if it is having less effect, if we are moving from the scalar relativistic calculation to the two component, then it's fine, right? Right.
Okay. I have the feeling, I might be wrong, but I have the feeling you're mixing two terms up here. Scalar relativistic means we neglect spin orbit. You can do that with the full.
Neglecting the spin orbit coupling, I mean.
So your question is your question really, do we need spin orbit? Is that what you're asking?
He's asking whether you mean that whether we need spin orbit or not.
No. That is not the question. I am saying if we are doing some calculation without spin orbit coupling.
Yes.
And doing the same calculation with spin orbit coupling.
Yes.
So in that case, do we need this picture change effect or not?
Okay, so you're asking with or without spin orbit, what's the reason, what's the effect of picture change? Wow.
Yes. That's it.
Wow, that's really beyond my expertise here. If I use codes, I trust that the developer have done it properly. Honestly, I don't know the answer. Absolutely not.
Actually, I don't know much about this picture change, and that's why I asked. Like,
yeah. Honestly, I have no idea. I mean, if you go into the books that I showed, the Auerbach's book or the fully full big books on quantum relativistic quantum chemistry, they have that kind of stuff. I know, but it's pretty heavy math, so I was probably too lazy to work through it. I don't know the answer.
Okay. Thank you.
Okay, there was some feedback here. Was there another question or not?
Yes, please come here. There is one more question.
Sir, could you give us a ballpark idea of what improvements to expect? For example, say, and also how much time, extra time. For example, Concham is n cube order scaling. So should we expect, say, around 10 times more time taken in calculations?
It depends strongly on the method. So I introduced briefly a bunch of methods. So if you do effective core potentials, you actually save a lot of time because you get rid of the core electrons. If you do a Hamiltonian like Zora or Douglas Cole like a two-component Hamiltonian in your favorite code, then the scaling then it's just another Hamiltonian. The number of integrals is pretty much the same, and your scaling still arises from your correlation method. If you do the full Dirac equation, yes, you have more integrals, but the scaling still arises from your correlation method. And so this comes down to more how it is implemented in the code. But again, scaling arises more from the correlation than from the relativity. Does that answer your question?
Yes, sir. And also, what is the say fraction of improvement attributed to say the scalar effects and the spin orbit coupling? For example, if we just treat spin orbit coupling in Concham, how much of the relativistic effects could we take into effect?
Right. This is a good question, and maybe I took that out of my discussions. Maybe I should have left it in, but the original slides, and I rushed through them, are from a 3-hour or 4-hour course, no more, from a 2-week course. Anyways, spin orbit. It really depends on the question you're asking. So if there are cases, let's see whether I have them on the slides. Let me check. Here. There are cases where you absolutely need it. Let me share this. One case is certain cases NMR. This is an extreme case. Here we look at the proton NMR in HF, HCl, HBr, HI. If you do a scalar calculation, you can just as well do a non-relativistic calculation. You get the same answer. To get the right answer, you need spin orbit. So there are cases where you need it, such as NMR here of the proton, and specifically people who did publish this. It's quite nice work. When they published this years ago, they found you need that if there is kind of a S contribution at the nucleus where you do NMR. Anyways, so there are some cases where you need it, spectroscopy. Another case, let me find this. Just check for it. Another case where you need it is, for instance, if you do any kind of spectroscopy, excited states, because you get the splitting of the levels. Let me see whether I have this here. Spin orbit coupling, yeah. So here are the slides. Yeah, maybe I should have left them in. I took them out. Because you get, as soon as there's something like a non-zero angular momentum, you get splitting of levels. And then excitation energies might go to the split levels, right? In structure, on the other hand, structure typically, the effect is pretty limited. So it's typically a scalar relativistic optimization is just fine. For thermochemistry, it depends on if the number of unpaired electrons stays the same between products, then you can typically neglect spin orbit. So here's an example. That's halogen molecules, so Br2, Cl2, and so on, right? And so you get the splitting here between 1/2 and 3/2 in this case of the pi symmetry, because it's non-zero angular momentum. The sigma symmetry is zero angular momentum. You don't get a splitting, but you get the splitting here, and you can kind of see if you have this closed shell case, you can kind of intuitively see that this averages out. So for geometries, it doesn't matter so much. On the other hand, if you do some kind of spectroscopy, say if you want to excite this one from here to here, or whether excited from here or from here, it does make a difference, right? Because of that splitting here. If you look at the dissociation energy, the atomization energy of these H2, Cl2, Br2, and so on, then again it matters because this is the atom, p orbitals of the atom, of the chlorine or bromine or iodine atom here, right? And because these are p orbitals, you have splitting, and for those two, the two just kind of cancel out to first order, but not for the last one, right? So it really depends on the question you're asking. So if you do energetics for a reaction where the number of unpaired electrons stays the same on the left and right, probably you're fine with neglecting spin orbit. If it changes, say if you do a redox potential, then absolutely you need it. If you do again, things like excitation energies to these split levels, then it matters. So it depends.
Okay, sir. Okay.
Good.
Okay, thank you, Professor Georg. So I think you can go to your Amsterdam AMS.
Yes, I will go to my AMS slides now. Let's do that. These are slides. It's like 5 or 10 minutes only, so I do it fairly briefly. Let me start them. Okay, and share. May want to turn off your microphone or again, there was feedback. Okay, here we are, AMS. And these are slides, like very nice slides from the Amsterdam people, from Fedor Gaumans, who shared them with me. He is kind of one of the outreach people of the company. SCM is the company that runs ADF. So these are kind of nice slides that show here excitation energies. Here stress strain in a solid. But that I'm not even sure about that. Oh, that's I think battery modeling or something. SCM is a company that runs ADF and more generally the Amsterdam modeling suite, which is more than ADF. Here's a little bit of history. It was started in the 1950s by Evert Jan Barends, who's still around in Amsterdam. Tom Ziegler, my PhD advisor, who passed away some 10 years ago. They were the kind of started that. And really with a focus to be able to do not just organic, but also inorganic chemistry. And they were really the first to do that. In 1995, they decided to start this company, SCM, as a spin-off company. At the time, honestly, I was a little skeptical if they went to commercial, but it really had the effect that there's good support, a good graphical user interface, academics, people writing their PhD see this. They're interested in new methods, but they're not less interested in the stability of the code. They just don't have the time, or in graphical user interfaces and so on. They also, in the 1980s, they also extended ADF to periodic code, which they call band for band structure. Later on, they added DFTB type binding, so semi-empirical DFT, Cosmo RS, which is, I have that on a later slide a little bit, reactive force fields, more recently things like machine learning potentials, and so on. So they're really aimed at both academia and industry. So this is a 2024 snapshot of where they are, and the old city of Amsterdam by the sea with this ring of canals. It's a nice place to visit, and quite a few people working there, plus typically PhD students with associated research groups. Some of them I've known for a while. Here's again Evert-Jan Barends, Stan van Giesbergen is the CEO, and several of the others here. With some of them we have worked. So in the last few years, they have built it as a complete platform, which they call the Amsterdam Modeling Suite, or AMS, as a platform. And so there's a driver, and the driver can run DFT up to MP2 at the moment. That's the beyond part here, both for periodic boundary conditions and for molecules. There's, as I said, semi-empirical reactive force fields, machine learned potential, and so on. And so the driver is kind of unified between graphical user interface, in my view, a really good one. Python scripting environment, we haven't used that much yet, so I can't really talk about that. So here's my view of this. So this is now my slide, not AMS slide. Again, there's a molecular code, ADF. I'll come back to it in a minute. Then there's a periodic code band, and because it uses atom-centered basis functions, it allows for just no periodicity, but you can also have periodicity in 1 and 2 dimensions and in 3 dimensions. If you do plane waves, you always have 3-dimensional periodicity by necessity. So there are other parts that were mentioned, Cosmo RS, which is a extension of Cosmo, as I said, tight binding, semi-empirical reactive force fields, and so on. Good graphical user interface. One thing not to take easy, they are very responsive. They are very good at support. Moreover, the code provides at least annual updates on this new development, as opposed to, say, Gaussian. I believe the last updates was when 03 or 09 or something, right? But I'm not going to pick on Gaussian here. There's in addition to the company, there's an active academic developer community. We are a small part of that. As I said, regular, at least annual updates and academic developer community. But as I said, also a lot of in-house scientists who do development. Barents and co-workers have published a new major paper that describes AMS. I was invited to be co-author there, and I'm very honored and proud of that invitation. So this is a major paper that describes the various features of the whole package, basically. Don't know how many pages, but it's a major undertaking. Right. Okay. IDS driver. So basically, again, that's one of their slides, combining the different levels, and then you can do at least a principal dynamics, frequencies, or phonons if you're on the solid stuff, stress, elastic tensors, Monte Carlo, etc. Right. So here's a little bit about the graphical user interface with a couple of snapshots. As I said, I think it works quite well. I am from that generation where we would write our input files exclusively in Unix or Linux or something. You can still do that, of course, but the GUI, the graphical user interface, provides you your input file and your analysis quite nicely. And if you need to, you can still, of course, go back to the actual input or output file. And there are various visualization tools and analysis tools and so on. So you can build your things and then and so on. As I said, as far as I can see, it's a really good graphical user interface. Here, scripting, as I said, I don't have much experience with that, so I'll leave it at that. Here, ADF, the molecular part. Unique points, it uses Slater orbitals. That's, as far as I know, that's the only code that does that. It has the immediate effect that if you use Slaters, you can't do analytical integrals. That's why everybody else uses Gaussian, so you use numerical integrals. But it's very consistent. These basis sets exist for all elements. We discussed relativistic. We have Zora as a principal relativistic method, although X2C is in there also. I haven't really tested it. We can do some of these solid state methods up to double hybrids and therefore MP2. Analysis is a real strength in my view. ETS NUCV, that's a version of the fragment type of analysis, energy decomposition analysis. QT-AIM is there, canonical MBOs, non-covalent interactions, and so on, various charge models, and so on. Also strong in various kind of spectroscopies. COSMO for salvation, SM12 for salvation, 3D RISM, we haven't used that. We haven't used that either. Subsystem DFT is kind of sketched here. Multi-layer, I haven't used that either. So here's my view of ADF, Slater type basis sets. As I said, numerical integration. Anybody doing DFT will do numerical integration, but typically only for the exchange correlation integrals. Here we do numerical integration for all integrals. As I said, Zora can be all electron or a frozen core, which is not the same as ECPs. It just means you freeze the core orbitals from an atomic calculation. And again, lots of different properties. And up to MP2 and various hybrids, various functionals. I mentioned Cosmos, Cosmo RS, these SM12s, these are important. Certainly for what we are doing. And again, I mentioned analysis being a really strong feature. Okay, what do I have here? This is one of their slides. I'm not, you can look at it, but I'm not going to spend too much time on it. It's basically on periodic calculations, band, you get the band structure out, and so on. And so, yeah, here's the band code according to SEM slides. They are also atom-centered basis functions, not plane waves, and these are Slaters and numerical atomic orbitals. And again, we can do Zora, so we don't need pseudopotentials, which then allows us to do core spectroscopy and so on. And there's a bunch of functionals that are available, but may have been extended since then. And again, we can do 1D and 2D polymers and add solvation if we so choose, or we can do surfaces and so on. And it's kind of true means here it is 2D or 1D periodicity. Good. There's a little more here that I skip over. And so here's my view of the band structure code. Said that already. Atom-centered, numerical, and Slater basis sets, which makes it much slower for 3D periodicity compared for plane waves, but competitive or even advantageous if you go to lower periodicity, because you don't have to fill vacuum space with basis functions. What I also like is that they are pretty similar between ADF and band, so they're kind of sister codes and really have very similar methods, and then can go from one to the other and has a bit of a continuum there. So numerical integration, Zora, similar property calculation, similar levels of exchange correlation functional, similar solvation models, similar analysis tools. Good. This is the semi-empirical implementation DFTB. I just show it there. We haven't used it. We have experimented with it, but I haven't used it. Partly because we are so interested in the actinides that are hard for semi-empirical methods. I know other groups who, independent of AMS or ADF, that try to parameterize these and have had limited success. Reactive force fields is also quite interesting because, of course, it's a force field, can go to very large systems and still have reactions. Again, I have no experience with that. What's that? That's their slide of putting various things together in the driver. Again, I'm going over it very briefly. And machine learn potentials, it's new. I haven't tested it, but that's certainly a really interesting approach to systems. Basically, machine learn your potentials and then run dynamics or large systems on your system, whether in AMS or elsewhere. That's certainly a good, interesting approach. Right, and that goes on here. Not going to go over that in detail since I don't have personal experience with it. But yeah, dynamics. Nice dynamics here. Right, that's solvation. Cosmo is something like this. As you probably know, Cosmo RS is the life work of Klimt and others. They have their own Cosmo RS code, which is closely related to Turbomol, ADF, and the Amsterdam people, SCM, they have implemented it in ADF and so on. So it's the extra parameterization that gets the solvation models more accurate on top of the electrostatic contribution. So basically, Cosmo RS stands continuum solvation model for realistic solvents. Again, that's the Reax FF. I'm not going to go over this in detail. This are some people that or stuff that they have worked on and companies they have worked with. And that's their slide. I leave it at that, except I wanted to show you two very small parts from our work just to focus on the analysis tool. Oh no, before that, I wrote a slide where what we have contributed in my group. First, in my PhD, now quite some time ago, I started the NMR and ESR module in ADF. Others have continued. That was for chemical shifts and G-tensors. And I did the first forces for relativistic, which is then the Pauli Hamiltonian that I showed you. Of course, that has been superseded by the Zora Hamiltonian. It's still there, but certainly not recommended, but at least we were able to do these trends that I showed you at the beginning, 3D, 4D, 5D metals, and so on. So that was my contribution back then. More recently, we have started to again do some method development, and was started by Craig Peoples, but is mostly the work of my current PhD student, David Samuel Michael, who some of you might know. And there we work on specifically the SM12 solvation model because it's a nice alternative to Cosmo. And for various things, it's better, or at least it's nice to have different methods to be able to shoot at that. We have single points in ADF with Hirschfeld charges and CM5. We are close to finished, or David is close to finished with the geometry optimization and the extension to the band structure code. David has implemented ESP charges, which make the geometry optimization, the forces better, and he's working on an extension to excited states, time-dependent DFT. And the other thing that David works is the constricted variational DFT. That was basically the last major project of Tom Ziegler before he passed away, and we have been interested to see, okay, where did they leave this off? So we have just published, just out at JCTC, published a major extensive benchmarking study to see what this method does compared to TD-DFT. And it's actually quite good especially for charge transfer excitations. And so therefore we are planning this is benchmarking, so we're planning some extensions. So that's my limited contribution to this project and code. I just want to give you maybe two examples of what we have done just with a focus on the analysis. So this is an older paper with an experimental group on uranyl complexes interacting with metals. And that's uranyl, that's uranium. So we need Zora, we need relativistic effects there. And that's kind of what this looks like experimentally. They put various metals here experimentally, and they were interested in what kind of bonding exists here, basically. And so there's a synthesis. I'm not even pretending to understand what they're doing, and I'm not going over it. But we look at bond lengths versus Mayer bond orders, first type of analysis. And we are interested in covalency. Shorter bond, presumably more covalent. So we kind of use this a little bit as a stage, and it has long been published. I didn't change that on this slide. So that gives us a certain order for different metals. Again, I'm not going to go over the chemistry here, but what's interesting is bond length versus bond order is kind of nice. Oh yeah, but the charges give the exact opposite trend. And normally you would think that shouldn't be the case. So usually higher charges would mean it's more ionic, less covalent. And just the opposite. What we found here is that this is largely ionic, but there's a little bit of covalency, and kind of if the charges are higher, the charges pull these atoms together, and then there's better overlap also. So we get relatively more covalency, but also stronger ionic character, which is kind of cool. And there's analysis. That's why I showed this here. Here's the bond critical points and QT aim and so on. So we get bond critical points. We are interested in that interaction specifically. But we see again that it's mostly still mostly ionic, so it confirms that. But the QT aim measures agree with what we see experimentally and what we get from the charges. We can also do ELF here. Again, it shows that it's mostly ionic. And we can use energy decomposition analysis. That's the one I wanted to get at. For these type of methods, you need to break your molecule into 2 fragments and then see how does it interact. And you break down the terms here. And so in this case, we choose a 2- and 2+ fragment. That's a choice you have to make. And so you get orbital terms, electrostatic terms, and so on. So again, the orbital and electrostatic terms kind of go hand in hand here. Okay. The other example I wanted to show is going a little more into this decomposition analysis. This is for separations. It's also published, but a little newer, here by former student Xiaobin Zhang. Again, molecules like this one here, how do they interact? And one of the things that's unique to ADF is the NOCV extension of this EDA analysis. That stands for natural orbital for chemical valence. So basically what you do is in EDA, I should have maybe written down the equations here, but you break down the interactions between 2 fragments into, as I said, electrostatic overlap or bond type of interactions, Pauli repulsion and dispersion. And then the overlap term you can break down by orbital. And that's kind of neat because you see here's your anneal kind of sticking in this page. There's a couple extra waters to fill the solvation sphere, and here's the ligand. And so you can attach energy contributions to these contributions here. And look at them and see, okay, that's sigma, that's also sigma, and also sigma, and then there's pi type interactions, and so on. And so it's really neat that you can break this down, and this is the NOCV method. That's unique to ADF. And then you can ask questions, okay, what happens if I change the ligand? Then turns out that some of the pi contributions become stronger or weaker, and so on, like here. There's also pre-organization energy. I left that. Right. So if we make it more rigid here, for instance, then we don't have a pre-organization energy, makes it better. And yeah, that particular pi contribution becomes much more strongly, so that presumably this is a better ligand for separations and for interactions here. So, but again, being able to break this down by the orbitals here, and then look for trends, that's pretty unique, I think. Right, so there they are, these orbitals. Right, and so what we also see here is there's clearly an F contribution. You can look at the canonical MOs here. So then it's relevant for separation. In this case, that's a specific thing. If we want to separate, say, americium from lanthanides, then the Fs would be there for the americium, but too compact for the lanthanide. So it might work for separations between actinides. Okay, and that was borne out experimentally. I'm not going to go into details. So that's my very short overview of that code. That's what I had for that, since I was asked to do that. Is there anybody else, anything else I can answer in questions or any discussions also?
So I just wanted to say that I just saw your paper appeared in JCTC on variational excited DFT, and now my group is also working on something similar, and we also got inspired by some of Tom Ziegler's 2014-15. It was very exciting that he was also following in the same direction that we are now thinking about. So it is very, very exciting. I have saved it. I have not read it yet, your paper, but it will be exciting.
Okay, thank you. So that we are competitors here, right? No, it's all good. Competition is always good for business. Yeah, then I should. I mean, Abigail told me about that a little bit, so I should be really on the lookout for that then. Good.
Okay. Are there any questions? Okay. It appears there are no more questions. So thank you, Professor Georg, for joining us and giving such a great overview of relativistic methods and ADF and your work. And sorry for the technical glitch that we had in the beginning.
That's always part of it. If people are interested, let me know. I'd be happy to share my slides.
Yes, that would be great. That we can share it with the participants. That would be great.
That's good. I just want to say, I'd be happy to share them. Just please don't share them further. Like, use them for your personal use before. At least ask me before you want to share them with someone else, please. Okay?
Sure.
Good.
Yes.
Then I'll do that. Yes, then I'll do that. They are pretty big, so probably we'll have. And actually, the slide set that I used, it contains a bunch more slides. It's the one that I usually use for teaching, but that's okay. Right. So yeah, I'll do that. We'll find a way to. We probably need. I don't think that works by email, but we'll find a way to do that. Okay. Good.
Maybe Google Drive. May work.
Something exactly. Something like that. I'll do it either today or maybe Monday. We'll see.
Sure.
Hope your workshop went well. Did it?
Yeah. So we have one more session tomorrow morning on kinetic energy functionals. So this is then tomorrow is the last day. So we had a very exciting workshop. I think participants have enjoyed it. Right.
Excellent. Okay, well then, good luck with the rest of the workshop. And it was my pleasure. I enjoyed talking about this. It's too bad I can't see any of you. Take care.
Yeah, that would have. Thank you. You have a great day.
Thank you. Bye.